Today, we are going to break down how you can dramatically boost your C# application's performance by mastering something called zero-allocation parsing. Now, if you've ever had to build high-throughput systems, trust me, this is a total game changer.
So let's start with a question that probably hits a little close to home for a lot of us. If you've ever done any heavy string processing in .NET, you've used string.split. It seems so simple, so harmless, right? But what if I told you it's secretly one of the biggest performance killers in your application? So here's our roadmap. We're going to start by uncovering the hidden costs of strings. Then we'll get into a really fundamental concept, the stack versus the heap. After that, we'll introduce the hero of our story, span T, see how to parse without making a mess, and finally, wrap it all up with a new way of thinking, the stack-heap partnership.
All right, let's jump right in. We're going to pull back the curtain on why some of the simplest, most common code you write can actually have a huge hidden performance cost. See, here's the deal. Those handy string methods like substring or split, they aren't free, not even close. Every single time you call one, you're creating brand new objects on the heap. This makes the garbage collector, or GC, work like crazy to clean up the mess, which can cause these horrible pauses in your app, especially when things get busy.
Let's look at a classic example, a simple configuration parser. This code looks totally innocent, but it is an absolute allocation nightmare. That first split, it allocates a new array on the heap. Then you loop, and inside that loop, every single pair.split call allocates another array. And then the keys and values themselves become new strings. It all just piles up, creating this giant mountain of garbage for the GC to deal with later.
Okay, so to fix this mess, we have to go back to basics. We need to understand the two places our data can live, the stack and the heap. I'm telling you, getting this right is the absolute key to writing high-performance code.
First up is the stack. The stack is incredibly, mind-bogglingly fast. Why? Because allocating and deallocating memory is as simple as moving a single pointer up or down. That's it. It's the perfect place for temporary data, variables that only need to exist while a method is running. Think of it as your super efficient short-term scratch pad. The heap, on the other hand, is for your long-term storage. It's for objects that need to live on after a method finishes, like that final configuration data we're building. Now that flexibility is crucial, but it comes at a price. Allocating memory is slower, and you've got the overhead of the garbage collector having to manage everything.
This visual really sums it up perfectly. The stack is for the fast, temporary journey inside a method. The heap is for the final, long-term destination. The big takeaway here is that you want to do as much of your work, the journey, on the stack as possible.
Okay, so now let's talk about the solution. And this is where a seriously powerful tool from modern .NET comes into play. Let's meet span T. The magic of span T is that it lets us look at and work with pieces of data without ever making a copy. Instead of creating a whole new string on the heap, a span just creates this tiny, lightweight window over the original memory. Under the hood, it's really just a pointer and a length, and it lives entirely on that super fast stack.
So, you might be asking, what makes this safe? How does it not blow up? Well, it's all thanks to that ref struct keyword. This is a special instruction to the compiler that enforces some very strict rules. It basically says this thing must live on the stack, period. You can't put it on the heap, you can't use it in async methods. These rules guarantee a span can never outlive the data it's pointing to, which is absolutely critical for preventing bugs and memory corruption.
All right, now for the really fun part. Let's go back to our parser and rewrite it using this new approach. You're going to love the difference this makes.
I mean, just look at this. It's night and day. On the left, the old way, a festival of heap allocations with split. On the right, we use read-only-span of character and the slice method. Every slice we take is just another one of those lightweight views. We create 0 new objects on the heap. All the hard work is happening on the stack, where it's fast and clean.
So what's the result of all this? The benchmarks are just staggering. We are talking about an 8 to 10 times increase in throughput. That is a massive, massive performance win.
And it's not just about raw speed. This approach also cuts down our temporary memory usage by an incredible 85%. That means way less pressure on the system and on the garbage collector.
And here's the real kicker. By keeping all that temporary parsing work on the stack, we have completely eliminated those performance-killing garbage collection pauses. That's right, 0. The GC doesn't even have to wake up.
This decision tree is the perfect mental model to use. As you're processing data, just ask yourself, is this temporary? If yes, use a span on the stack.
Then, when you're all done, you ask a second question. Do I actually need to store this result for later? Only if the answer is yes do you finally create a real string on the heap. It gives you one single, controlled allocation at the very end, instead of 1,000 tiny ones along the way.
And that brings us to our final and maybe most important point. This isn't about trying to avoid the heap completely. It's about a new, smarter philosophy for how we manage memory in C#.
So what's the playbook? It's simple. Use spans for the work, for the processing. Use strings for the final storage. Keep all your temporary stuff on the stack. Only move data to the heap when you absolutely need to keep it around. Trust the compiler's ref struct rules to keep you safe. And maybe most importantly, always profile your code. Find the real bottlenecks before you start optimizing. The goal is not zero allocations, it's smart allocations.
This quote from the source article just nails it. The stack is for the journey, the heap is for the destination, and span T is the high-speed bridge that connects them. By understanding this partnership, you can build systems that are not just fast, but that scale beautifully. The question to ask isn't, how do I avoid allocations? It's, how do I allocate intelligently?